This video is a quick review on exponential applications, so word problems with exponential functions. The first thing we talked about when we talked about exponential applications is the difference between factor and rate. So remember when we talked about the factor is the base. So what we see in our problem. Okay, it's going to be what we see in our problem. That's our factor. Okay, remember factors are things that we're multiplying. So what you already see is what's already being multiplied. Your rate is the difference of your base from 1. So we'll do some subtraction. Okay, how far away from 1 is your factor from, is your base from? So I wrote down a few examples here, so maybe you pause the video and take some time to copy them so you have some notes to look back to study for your test. So it says name the growth and decay factor and rate for each problem. So looking at the first problem, I know that this is going to be a decay. I know it's going to be a decay because my base is less than 1. Okay, so I know it's a decay factor and a decay rate. Well, that factor is going to be 0.80, that's my base, and the rate is 0.20 or 20% if it were written in a word problem. Because I know that 80 is 20 points, 20 percentage points away from 1 or away from 100. The next problem here, looking at my base, I know that this is a growth factor because my base is greater than 1. So my factor is what my base is. My factor is 1.25. And my rate is the difference from 1. So how far away from 1 are we? Well, we're 0.25 away, or 25%. Okay. So here again, another example, looking at this base here. That's a decay factor because that base is less than 1. And my factor is my base. So that's 0.24. And my rate is the difference from 1. So I want to say 1 minus 0.24. So I'll take my calculator, 1 minus 0.24, and that's equal to 0.76. Or we can change it into a percentage, 76%. Last one here, looking at this base. It's a growth factor because that base is greater than 1. The base is my growth factor, 1.06, and the rate is the difference from 1. So 0.06 or 6%. That's going to be very important to know the difference between growth factor and growth rate, decay factor and decay rate. I'm then going to go into your exponentials packet. It's page 28 if you haven't finished it, and I'm going to work on some of these examples here. I'm going to eliminate the middle few, and I'm going to work on the first 6 and the last 6, reminding you on how to set up exponential growth and decay word problems. Okay. So the annual sales for a fast food restaurant is $650,000, and it's increasing at an annual rate of 4% per year. So let's break this down. So we have an initial value. We see this word increasing, that tells me the plus. We see a rate, we see 4%, and we see a time, 5 years, right? So, and this is time. So when we see this word increasing, we know we're going to use this formula, y equals p times 1 plus r raised to the x or raised to the t time. Okay, so that word increasing tells me to add. I know I'm using this version of our application formula, our growth formula. So I have 650,000, that's P. I'm always going to have the 1 plus, especially when it's increasing. So that plus is increasing. Remember, for our percentage, our rate, we have to change it to a decimal. You move it 2 positions to the left. Some of us were missing this on our practice. 1, 2. So that's where the decimal goes, where that arrow ends. 1, 2 to the left, always 2 to the left. So 0.04, and that's going to be raised to our time, and it said after 5 years. So after you write the equation, you can substitute it into your calculator and find your answer. So 650,000 times 1 plus 0.04 raised to the 5th. And I get 790,824. And I'm going to round to the nearest penny. That's the nearest penny. Okay. The 100th spot of our decimal to the nearest penny. So let's work on these other growth problems. I know they're growth problems because I see the word increasing. That's growth. I know it's a growth problem because I see an annual growth rate. That's plus. So I'm starting with 800 students, and I know that we are adding because of that word increasing. We see a percentage of 2%, but we have to move that decimal over 2 places to the left. So we'll say 800 times 1 plus 0.02 raised to the 6th. And notice it says students. So the answer I get in my calculator is 900.93. But we're not talking money anymore, we're talking people. So we round to the nearest person. This is students for this problem. Again, we have a growth. There are 70 northern sea otters. We know we're going to be adding because of that annual growth rate. That tells me to add. I have a percentage of 18%. So that 18%, just so you can see me move the decimal, that decimal is always at the end of a whole number, and I'm moving it 1, 2 places to the left. So that's going to be 0.18 raised to the 4. So this is going to be 70 times 1 plus 0.18 raised to the 4. And again, we're talking about a living thing, sea otters. So I have to round my final answer when I get it into my calculator. Okay, if you're following along to practice using your calculator. Let's skip down to question number 7, 8, and 9. It says write an exponential decay function. It gives it away for you, but I'm going to highlight some of these key words here that I know are going to tell me to be subtracting. So in the first problem here, we see the word decreasing. That tells me to subtract. Okay, we have this word decreases. Again, it tells me to subtract. Here in this specific example, we have this word half-life. And that word half, that's a fraction less than 1. So we know it's got to be a decay. So if I'm using that decay function, nothing changes from my equation up top except that instead of adding, I'm now subtracting my rate because decreases, half, I'm taking away from these things. So A population of a town is 2,500, so that's still my initial amount, 2,500. And I'm still going to have the 1 a part of my equation, 5 years. We already said it's going to be decreasing. We highlighted that keyword that told me I was subtracting. And now I have a decay rate of 3%, so that's 0.03. So 2,500 times 1 minus 0.03 raised to the 5th. And we're talking about a population. So the number I get my calculator looks like this. But since we're talking about people, we have to round it to the nearest whole person. So that's going to be 2,147 people in this town's population after 5 years. The next example here, the value of a company's equipment is $25,000. I always have the 1 in my problem. Now we're going to 8 years. We're subtracting because we already highlighted that word decreases. So we have a rate of 15%. So again, when we have a whole number, that decimal's at the end, move it 1, 2 decimal places. So that's going to be 0.15. Raise it to the 8th power. And now we're talking about money. So we're going to round it to that nearest cent, that 100th place. And so that's how much money you should get. Okay. This last problem, the half-life of iodine, is approximately 8 days. Find the amount of iodine left from a 35-gram sample after 32 days. So this rate's going to be a little bit different. So we have find the amount of iodine left from a 35-gram sample. So this is our initial amount, 35 grams. I'm going to put my 1, and we have a subtraction sign because of that half-life. Well, if I'm taking half, that makes my rate 50%. Okay? And now I have to figure out my time. Well, I'm taking half of it for 8 days, or every 8 days. So it's like, I get to the 8th day, half of it is gone. I get to the 16th day, half of it is gone. I get to the 32nd day, half of that is gone. So we're doing it so my time is 32 days total, but it's every 8 days I lose half. So how many days total is this thing dying off is what we're trying to figure out. So 32 divided by 8 is 4. So my time is 4. So we'll say 35, 1 minus 0.50 raised to the 4th. So we have approximately 2.19 grams left of this sample after the 4th trial, after that 4th experiment. These were some flash examples on the exponential growth and decay applications. If you need more explanation and examples, please visit previous videos.